Hello again. Welcome to the next edition of NPTEL online certification course on CMOS digital VLSI design. We will be starting the combinational logic design module 7 now. In our previous module we have seen certain things which I will just recapitulate and then we move forward. What we have seen was that if you use a pass transistor logic, your voltage levels were falling, and if they fall below the switching threshold of the subsequent block or the subsequent gate, then you require to restore the level of the initial value, right. So, and you try to make it above the switching threshold for that particular matter. As we have seen earlier in our previous discussions that this if you look at this point, if you look at this whole discussion here, you will see that that we had seen that you had a drop of VDD minus VTN, right. We had seen already this drop available to us. Now, as I discussed with you previously, if this is therefore 0 and this is 1, then this is cut off and therefore this remains as 0, but if it is a 1 here, I will get 1 minus VTN, right, and as a result this might be low. When this becomes low, this becomes on, and when this becomes on, this VDD starts to charge this and tries to make it to reach to VDD, and we have already seen this point. We have also seen that if W by L ratios are large, right, you have a change in the logic. Therefore, level restoring circuits, which is this one, is primarily a ratioed circuit. So, it is a ratioed circuit, primarily meaning that the aspect ratio of the pull up transistor is critical in the functioning of the level restorer circuit. So, that is an important or key switch to take over from here, that this is basically a ratioed logic, right. It is a ratioed logic, which means that W by L of P plays a critical role. P means in this case the restorer, but as you can see, higher W by L will imply a larger ID flowing through this path, right, and therefore faster restoration of logic at X. This is understood, but please understand one critical issue, that as you start to make the W by L ratio of MR larger and larger, the capacitive loading here, which is this one, will also start to increase, because this X sees a larger capacitive load, right, and therefore as you make the W by L ratio large, though the current taken to charge this to VDD is also higher, but then the capacitance value or the capacitance seen by this node also raises. So, the capacitance value becomes larger, right, and that is the problem area which comes into picture with the larger W by L ratio. So, as you can see in this slide here, the higher the W by L which I made, the voltage was actually restored to its original value to a larger extent, right, expected also in a longer run. We have also ensured that the sizing of MR, right, MR is this one, and MN, which is this one, will try to make the logic at X change, right. For example, if MR is stronger as compared to MN, restoring the level at X will be faster, whereas if MN is stronger as compared to MR, de-restoring will be more or denigrating the signal at X will be a much more important issue. So, therefore, W by L ratios are important, and therefore, it is also known as a ratioed logic indirect. With this knowledge or with this idea, we can actually therefore explain or understand that this level restorers are generally used. You can also have, for example, 2 PMOSs in parallel to each other in the level restorer. So, this is the in-out feedback path which is coming, and it drives, rather than 1 PMOS, it drives to 2 PMOSs. So, it drives 2 PMOSs. What does it, why is it advantageous while driving 2 PMOSs is that the currents will be larger, because the effective resistance in the pull up path will be R by 2, and therefore, even with a lower W by L, I would achieve a larger current flowing through the system, and therefore, the node X will be restored at the same rate as the previous case. Only thing will be, you will have now a smaller time to do that. right. So, this implies that you have a reduction in the resistance available to you if your restorers are. So, if this is MR1, this is MR2, then MR1 and MR2 together will form a composite device which will lower the potential at this particular point at a very fast pace. Coming back to the concept of power dissipation, please understand the power dissipation here is very, very small, and the reason being there is no static power dissipation, almost zero. The only problem is that the rate at which the data can flow into the system will be actually limited by the TP or the delay of this inverter block, right. So, if your delay of this inverter block is very high, then it takes a finite amount of time for the signal to go here, switch on the value of MR and restore the level of X to a higher value, right. So, therefore, the rate at which the data comes at this point will be finally determined in terms of level restorer working fine or not upon the actually the propagation delay of this inverter block, right. So, with these are the key basic issues which people face or people have a problem when they are dealing with level restorer circuitry. So, level restorer is helpful for all your pass transistor logics, right. We come to the next one, and that is known as a multiple threshold transistor concept here. This is also referred to as a swing restorer pass transistor logic. So, this is basically a swing restored PTL pass transistor logic, the swing restored pass transistor logic. And what we do is that we use multiple VT devices, multi VT devices, rather than using a single VT, we use multiple VT, right. And the idea is something like this, that so I have a pull up, so I have two inverters. So, this is basically two inverters connected back to back, right, almost like a memory unit. So, I have got two inverters connected back to back, and therefore, once the data is latched here, it will latch. So, if this is 1, this will be 0. I think it is clear to you that these are basically two. So, it is basically something like this. It is I have got one inverter here, right, another inverter is something here for the pull up case, and then I have got this. So, if I have 1 here, I will have 0 here, this 0 comes here, I will get 1 here, I will get 1 here, I will get 0 here. So, this is basically a latch, right, and this latches the values at this point as x as 1 and x bar equals to 0, and it will remain like this until and unless you overwrite it by a external source by a new value, right. So, if you go back to this slide here, this part which you see in front of you is primarily the PMOS pull up part, or the basically the inverter, and it stores the data, whereas pull down part is composed of NMOS transistors, but obvious, and complementary inputs are given to gate and source drain terminal, right. To gate and source drain terminal we give complementary inputs, and complementary output is available to you by out and out bar, and we latch it using these two values. So, what primarily this device does is that it tries to latch the value at a much faster pace in the pull up case and latches it to the value which you have defined by virtue of the input signal given to the complementary pull down conditions. Let me show to you a basic XOR XNOR complementary logic. XNOR OR, so it is basically a 3 input logic gate, and it is basically a pass transistor logic. So, let me draw for you, right, and I will explain to you what these terminologies are. So, this is C bar, this is B bar, this is A, right, A, we have then C, and then from here we do B, this is B, again I have A here, but this is A bar here, and then I connect this to this, and if you go this side I have got C here, and then I have got sorry. So, let me show to you that I have got here C, right, this is C, and then you have got C bar here, right, this goes to B bar, this is A bar, and similarly this will come to B, and this is A. So, this is B A, this is B bar A bar, and let us see how does it work out in terms of this actually going to this direction, right, and this actually going to the. So, you see this will be going where this will be coming like this, this will be coming like this, and then this will be going like this. So, this is your out bar and this is your out. So, whenever your A and, so you see very well, this is basically your XNOR PTL logic. So, this is basically your swing restorer PTL logic. Why it is swing restorer? Because these two latches here, which is basically here, tries to restore the swing to VDD and ground. So, any pass transistor logic lowering the swing, this pull up two inverter pair will actually pull it up to a much higher value and try to latch it to that higher value available to you. The only problem which people face in pass transistor logic, as I discussed with earlier, was that you always have a VSB, right, because please remember, in conventional CMOS architectures, my source was grounded or connected to the most negative terminal. This ensured to me that threshold voltage change was 0. But in this case, if you see carefully, that you are applying a potential at source end. So, your VSB is not equals to 0 at any point of time, because source and bulk now are relatively at very different voltages. As a result, the threshold voltage will change, right, and that is quite critical. I will give you an example to show, to just give you an example. Let us suppose this is A, right, and this transistor is there. So, let us suppose this shows a 1 here, A equals to 1, voltage here rises, VSB becomes larger, there is a change in the threshold voltage here, which is, let us suppose it was initially VT1 was equals to 0.5 volts, now let us suppose it has become 0.3 volts, right, VT2 after the change. So, you require a lesser amount of voltage to do it, fine, or reverse, if we let us look at the reverse first, suppose it becomes 9, but your B bar which you got from some place, its value of voltage is just 0.6, because he knows for sure that 0.6 will switch on the value of the will switch on this transistor, but by virtue of VSB the threshold has now shifted to a higher value, let us suppose, and therefore B bar has to be at least 0.9 to switch it on, then the whole functionality of this swing restorer PTL fails, right, and it will not work properly for you. This is one important point which you should always keep in mind. The second important point here is that A, B, C, I am assuming that A, B, C and A bar, B bar, C bar is all available to me. So, all these 6 signals are available to me. For availability of the complementary signal, if you remember, we require a static transistor, and therefore, just to have 3 signals and 3 complementary signals, we require 3 CMOS inverters, which primarily requires that we require 6 transistor extra. So, that extra count you should keep in mind while discussing pass restorer logic, right, and that is what I was just trying to discuss with you in this case. We came to the last type of logic. We used swing restorer, one of them. We used the second case in which we had the pull up and we had CMOS inverters which connected back to back, which was able to pull the whole voltage up to VDD and push it to ground, right. The third one, which is being very seldom used in digital logic design, is what is known as the transmission gate logic. I will explain to you what transmission gate is, and we can see one by one how it works out. We have already discussed that NMOS is a good strong passage of 0 and PMOS is a strong passage of 1, right. If I replace NMOS, PMOS by a single unit known as transmission gate, and I will say show you how, I can actually have my voltage being not almost constant, independent of everything else. So, there will be, so it will be good, it will be a strong passage of 1, it will also be a strong passage of 0. So, both will be passed very strongly by transmission gate logic. And how, what is the transmission gate logic? I will just show it to you by this diagram which you see in front of you, which is here, right. So, let us suppose A is 1, right, A is 1. Then if let us suppose C is equals to 0 or 1, then if C is equals to 1, since C bar will be equals to 0, this PMOS and this NMOS and PMOS will be both on, and A will be equals to B will be equals to 1. I will explain to you what, otherwise this looks very complicated, but let us me just show it to you. So, I have something like this, I have got an NMOS here, right, I have an NMOS here. So, this is a source, this is your drain, this is your source, and then connect to it PMOS, right, which is something like this. and you connect this with A, let us suppose, and this is B, right, and then this is you apply C and this is C bar. So, you apply complementary signals here and here. So, X is equal to Y complement sort of signal you apply. So, whenever C is equals to say 1, A equals to 1, C bar will be equals to 0, this NMOS will become on and this PMOS will become on, and as a result 1 will be transmitted to this B and B will be read as 1, or if it is 0 it will be read as 0. If either C is 0 and C bar equals to 1, this will be also off, this will be also off, and therefore, this will be in a high impedance state. So, B will be in high impedance state, right. So, the transmission gate helps you to transmit a signal without any degradation of the signal, and what is the logic behind it? Very simple. Since I have got a NMOS and PMOS in series to each other, right, in parallel to each other, we will see that the compound device which you see, the ill effects of passing 1 and zeros will be actually removed in this case. So, just to give you an idea, and this is the schematic which we generally use in our locality, that this is basically looks like this. So, this is basically your NMOS, right, and this is effectively your PMOS, right. So, I have an NMOS here, I have a PMOS here for our practical purposes, right. So, let me come to therefore explain to you that how does therefore so this is what we get from this side. Now, I will just show you how it works out in a detailed manner, that say I have an NMOS and PMOS pair, something like this, right, and this is C bar equals to 0 and I give C equals to VDD, right. I have got A equals to VDD and therefore B will be initially 0. Suppose I have a CL and this is grounded, right. So, initially let us suppose it was 0 initially, and you this was all off. Now, what you do, you give C equals to 1 and therefore C bar equals to 0, and therefore, this will rise to a value equals to VDD, but obviously will rise to a value equals to VDD. The idea is that this is an NMOS, right, this one is basically your NMOS, it is a very strong puller of 0, right. So, if this is VDD, right, let us suppose this is gate obviously and this is source, right, or maybe this is, yes, maybe it is a source, let us suppose, or if you want to put it drain also does not matter, but this source, then VGS, gate to source voltage, will be 0. If it is 0, it implies that I cannot switch on the device because my VGS should be actually greater than or equal to threshold voltage of the device, VTN. Look at another sense, if I connect this to the drain, this to the source, and similarly this is the drain, this is the source, then at such a stage when initially it was 0, then VGS was equals to VDD, which is basically larger than VTN of NMOS. This switches on the device and therefore, a current starts to flow, charging it to near VDD. As it starts moving towards VDD till VDD minus VTN, right, till the voltage rises to VDD minus VTN. After this, the NMOS goes to from saturation it comes to the linear region, and therefore, after this it will come to cutoff below this. But then please mind, by that time the drain to source voltage of PMOS is such that it has actually crossed mod of VTP, and therefore, this has turned on and it is into the saturation region, and therefore, there will be current flow because of this. So, the idea here is that by simply manipulating the values of the charge carrier or the current, by virtue of the fact that for a device to be in on state and in saturation, VGS should be greater than VTN for on state, and I should also know that VGS minus VTN, VDS should be greater than or equals to VGS minus VTN for it to work in a saturation region. With these two conditions, condition 1 and condition 2, I can safely say that that I can have a current flow between point A and point B of this network, right, assuming that initially you had 0 value available in this case. With this basic understanding of transmission gate logic, let me show to you how a multiplexer can be designed using a transmission gate. I suppose multiplexer is clear to you. Multiplexer means that using a control signal, I can actually allow certain signals to cross through and then disallow certain signals. So, if you have got 3 input signals available to you, then by using certain pair of select lines I can allow only one of the signals to pass through and all others to block, right. So, this is basically a multiplexer design. If you look closely to the left hand side of this one, do not worry about this. This is basically the layout which we use. I am not discussing at this stage this layout. This is basically the layout of a TG logic, also known as transmission gate. If you very closely look here, it is basically if S equals to 1, right, S bar will be equals to 0, right, and therefore A will come here, right. If S equals to 1, this will be S bar, this is S also. So, if this is 1, right, then this is 0, agreed, this will be 0 and this will be 1, and therefore this will be off and this will be on. When this is on, A will be transmitted to this point and A bar will appear. So, F will be equals to A bar. Now, if S equals to 0, right, so I get 0 here, so I get 1 here. If it is 1, then this becomes on and this becomes off. So, this becomes on, this becomes off, right, and B gets transmitted here to the output side, B bar, sorry, B bar gets, because I have a static inverter also available with me. So, therefore, by having 1, 2, 3, 4, 5, 6 basic transistors NMOS and PMOS, I am able to design a 2:1 mux. So, this is basically a design of 2:1 mux for all practical purposes, and this works very fine for transmission gate logic, right. The only thing which you should be careful about, and that is very important as far as designing with TG, is that you should ensure that S and S bar or C bar, which is basically the clock, right. So, what I am trying to tell you is something like this, that if you have a transmission gate logic and the transmission gate logic has got something like this, right. So, this is C equals to 1 and C bar equals to 0, then you have to ensure that C equals to 1 and C bar equals to 0 happens exactly at the same instant of time. So, C equals to 1 means like this, C equals to 1 and then it goes to C equals to 1, then C equals to 0 is something like, let us suppose this, it goes like this, it stays 0 here, right. So, they should be complementary in nature and there should be no overlap. So, let us suppose I have C here and I also have C1 something like this, right, or something, I have C1 here, suppose C equals to 1 here, right. I want C bar to be equals to 0, right, I want C bar to be equals to 0, but what is happening is that let us suppose C bar is not equals to 0, it is something like this, this is C bar, let us suppose, by some reason or another, then I do have a corresponding path where both C1 and C bar are both equals to 1, and that means that if both are 1, then either of the devices will be on, not both of them will be on. You are getting my point. So, if you allow only one of the device out of PMOS and NMOS to get on, then you have to also ensure that then you will automatically see that the NMOS switches off at VDD equals to VDD minus, at VGS equals to VDD minus VTN, and the same thing happens to mod of VDP when you are using PMOS. So, it will not work and give you a linear profiling for the whole range of voltages. So, you have to ensure that they are just mutually non-overlapping signals, and the more further the problem is further actuated by the fact that since C bar will only come from C if you put a static inverter. So, this will be C bar. So, there will always be a delay associated here, right, and this delay will actually then change the values of the output voltage to output logic level to a larger extent. So, this is why I just wanted to give you an idea about how a transmission gate logic works and how does the transmission gate help you to achieve the factors which you want to do it, right. After this, let me therefore give you an idea about how a transmission gate actually, why does transmission gate give you almost a profile of output voltage which is almost fixed. Look at this slide, look at the slide in front of you. So, as I discussed at the very starting of this module, that any transistor when it is on state will always behave as a resistor, right, but the problem is that the resistor which you get will be a function of the input voltages, because at one time it is saturation, another it is non-linear, another is linear, another is cutoff. So, all these 3 states will have 3 significant values of resistances, and they will vary with respect to the input voltage. So, what we do here is the effective resistance which you see is modeled as a parallel connection of Rn and Rp. which is basically the NMOS and PMOS resistance. So, Rn is basically the NMOS resistance, right, and Rp is basically the PMOS resistance which you see in front of you. Now, if you see Rp is given by this formula, do not worry from where it is coming at this stage, and Rn is given by this formula which you see in front of you, right. As you can see here, when my VDD minus, so if you look at this point, if you look at Rp, as VDD minus mod of VTP becomes low and low, right, Rp goes on increasing. So, you look at this graph which you see in front of you, this one on the right hand side, as V out increases, right, as V out increases, this VDD minus VDD term so becomes larger and larger, right. As it becomes larger and when let us suppose when V out increases, then what you see is that V out means this is V out. So, this voltage increases, this is increasing, then your Rp will go on falling, because why? Because V out is increasing, right, and as a result VDD minus V out will be smaller and smaller, and the Rp will be almost a linear fall available to you. So, the red curve which you see in front of you is basically the variation of Rp with respect to the external voltage, which is V out in this case. Just the reverse happens for Vn. In Vn Rn is the resistance offered by the NMOS transistor. So, if you look at this Rn, as the voltage increases, output voltage increases, Rn actually starts to increase, because I think I can make it clear. See, when VDD increases or the output voltage increases, VDS starts to increase. If you go back to your very basic IDVD characteristics of an NMOSFET, it was something like this as you had plotted. Remember that if you plot VDS versus IDS, right, drain to source, then initially my resistance was small and then it becomes infinitely large at this point. At this point it is almost infinitely large. For ideal case infinitely large, if you have channel length modulation effect, you will have a value of Rn which is finite value, but will be always less than the infinite value. So, therefore, as you increase the value of VDS beyond the point which is given by beyond the point VDS equals to VGS minus VTN, you enter into saturation and the resistance suddenly becomes very large. So, if you therefore plot the value of Rn with respect to V out, you can see that it will be sort of an increasing value, whereas Rp will be actually almost like a decreasing value. So, this is Rp and this is Rn, right. So, if you take these two together, I can get a profile. So, this will be nothing but Rp parallel to Rn, and that is what I was showing you here, that if you look at the green curve here, I can just delete this whole thing, erase all this thing. Then if you look at this point, this green curve is basically the parallel combination of Rp and Rn. As you can see, this is almost flat, which means that the resistance is constant independent of the value of V out. Since the resistance is constant, the value of voltage available to you in the external part will be also constant, and it will be lower than both Rn and Rp. If you look very carefully, this Rn parallel to Rp will be less than the least. As you know, two resistors connected in parallel will always be less than the least. When it is so, you automatically get a resistance which is much smaller as compared to the previous two cases, and therefore, there will be a good transmission of either 1 or 0 from one point to another, right. So, this takes care of the value of the pass transistor logic. So, to recapitulate, let us see what we did. To reduce the transistor count, what we did was to reduce the transistor count here, we had preferred what is known as a pass transistor logic, right. But then pass transistor logic has got difficulty to drive the next stage properly. The reason being, there will be a drop in the voltage available to it, and it might be even lower than the switching threshold of the subsequent block, right. And as we see that if it is connected in cascade, you do have a problem of transmission. Now, if you have a differential pass transistor logic, also known as swing pass transistor logic, then both true and its complementary forms are accepted, and both out and out bars are also produced. We can remove the problems of pass transistor logic by using level restorer, by using a PMOS in the pull up case, but as I discussed with you, changing it's a ratioed logic for sure. So, this will be a ratioed logic, right, and therefore, MR by MR, the ratio of W by L of MR will be playing an important role in determining the functionality of the of the level PTL level restorer. We also use a multiple threshold transistors in the path, and we also use, finally we ended up with transmission gate concepts. So, what is basically a transmission gate, and how they are this. But the final idea here is that it might look to you that PTL, or for that matter DC-VSL, are much robust as compared to CMOS, less transistor count, but until and unless you have very strong reasons to go for all these types of networks, still complementary CMOS technology, which we have used till now, is the best technology, and complementary CMOS design is the most preferred design. So, rather than using pass transistor logic or even transmission gate logic, so it is better to use the previous case which we developed, right. The cost we are paying for it is though it is a lower transistor count, but the cost we are paying for it is that we need to have signal complementary bars. It is becoming a ratioed logic, which was not earlier, and you also have a problem of reduced noise margins. So, with this we finish off the concepts of pass transistor logic and how to restore the levels of pass transistor logic, right. We will do in the next module what is known as dynamic logic. So, we are finished with static logic, right, and we will do dynamic logic after this one. Thank you very much.